Imagine an astronaut standing before a window, seeing a golden doorway floating beyond the darkness. That planet looks almost like an open gate, but it is actually far beyond human endurance. Saturn lies on average about 1.4 billion kilometers from the Sun, many times farther than Earth. Even sunlight takes more than an hour to reach the cold region around those rings. A robotic spacecraft like Cassini once needed nearly 7 years and several gravity assists to arrive there. By normal logic, a soft body needing water, air, and gravity should not be there. Deep space is not an empty road, but a place where every living condition is stripped away layer by layer. If life support stops for a few hours, a once safe cabin becomes a dangerous box. If radiation shielding is not enough, the silent void itself can pass through living tissue. If one part fails midway, Earth becomes only a place sending signals too late. Yet humans still draw flight paths, build spacecraft, test sealed chambers, and dream of distant planets. They have sent robots there, heard winds on Titan, and seen ice erupt from Enceladus. Machines can sleep, endure isolation, and work in cold that the human body cannot bear. That is Saturn, the golden doorway facing distance, radiation, and the biological limits of humankind. The question is not only reaching that place, but surviving long enough to see it. The origin of the problem begins with one simple fact. Earth gave birth to humans too close to home. Every cell, blood vessel, and breathing habit was shaped by Earth's gravity and atmosphere. Saturn lies in a part of the solar system where light is weak, heat is low, and return is long. For robots, a long flight path is an energy problem. For humans, it is a survival problem. There are no rest stops, no nearby hospitals, and no supply trucks between planets. Successful crewed missions have mostly stayed near Earth, where rescue can still be imagined. Reaching the moon was a giant leap, but still only the suburb of the old home. Mars is already hard because it takes months, while Saturn pushes time into another scale. The longer a mission lasts, the quiet fatigue of machines and humans silently grows. Every travel day needs clean air, clean water, food, stable temperature, and a clear mind. On Earth, nature does most of that for free. Out there, everything must be engineered. The farther from the sun, the weaker solar power becomes, making each panel less useful. So the journey needs not only a powerful rocket, but a sealed home that can run itself. That home must resist vacuum, radiation, freezing cold, fire, microbes, and isolation. The farther a place is, the less an error remains a small incident. It becomes a trapped process. Saturn is also not a destination with ground, a runway, or a natural harbor. It is a giant gas world, stunningly beautiful, yet offering no place for human feet. If humans reached the Saturn system, they would have to live in ships or around alien moons. But even those moons only change the form of danger. They do not turn the place into home. So the story begins not at Saturn, but inside the limits of the human body. Humanity's first response to space was to wrap itself in an artificial shell. A spacesuit does not make a person stronger. It only carries a piece of Earth along. The first spacecraft were the same, small pressure chambers keeping humans away from vacuum. They suited short trips, where everything was measured in hours or days. When time stretches longer, that small shell must become a living environment with its own rhythm. Humans learned to recycle water, filter air, and force waste back into resources. But recycling is not magic. It is a chain of machines that must work almost continuously. A clogged filter, a stuck valve, or a false sensor can change the whole cabin's condition. To fight muscle loss, astronauts must exercise, because the body mistakes weightlessness for rest. Bones are also not used to carrying no weight, so they slowly lose the signal to maintain themselves. Those exercises do not turn a spacecraft into Earth. They only slow the decline. The mind must adapt too, because deep space has no streets, seasons, or strangers passing by. Stations around Earth became laboratories for those biological and psychological reactions. But those stations still receive supplies, rotate crews, and fly under the planet's protective umbrella. A journey to Saturn would leave that familiar region and outlast every habit of rescue. So the first adaptation is only learning to live temporarily inside what was never meant for life. Every early victory relied on shrinking Earth into metal, plastic, and wiring. But the more a world is compressed, the more each remaining detail must carry. A ship to Saturn cannot be merely a vehicle. it must be an artificial ecosystem. And when an ecosystem is manufactured, the next question is, who keeps it from collapsing? From here, the journey is no longer a launch. It becomes a long-running operating system. Engineers must stack each layer: launch, escape, orbit, cruise, brake, and survive. Each layer needs its own fuel, mass, schedule, and safety margin, with nothing added casually. Rocketry has a paradox. To carry more, a rocket must burn more just to carry it. So the road to Saturn is usually not straight, but a dance around planets. Gravity assist is like borrowing a giant push, but it requires arriving at the right place and time. For robots, waiting years for an orbital window can be acceptable. For humans, time is biological cost. A crewed mission must carry extra food, water, medicine, repair tools, and radiation shelter. Everything added helps survival, but also makes the ship heavier and the flight harder. Systematizing means turning fear into procedure, and procedure into design. The ship needs sleeping zones, work zones, medical areas, solar storm shelters, and spare parts storage. The ship also needs decision-making software, because commands from Earth are no longer immediate. When commands arrive late, the ship must recognize faults before people on Earth even understand them. Medical data must also be monitored continuously, because the body is living inside a long experiment. Without a full group of specialist doctors, the crew must become technicians of their own bodies. The spare parts store must predict failures that have not happened yet, in a place with no replacement shop. A fan, a water pump, or a small connector can decide the breathing rhythm of the entire ship. The ship also needs a thermal strategy, because weak sunlight and hot machinery create a narrow balance. Too hot, equipment weakens. Too cold, fuel, batteries, and materials can lose stability. Everything must work like a sealed orchestra, where one mistimed instrument bends the whole composition. But halfway through the journey, the golden doorway is no longer merely distant. It demands absolute precision. If the ship arrives too fast, Saturn cannot capture it. If it arrives at the wrong angle, fuel disappears. Braking around a giant gas planet is when the dream must pay in real energy. For a robotic craft, failure means lost equipment. For astronauts, it means losing a small living world. The more complete the system becomes, the deeper the question: how long can it work before it tires? The first central mechanism is orbit. In space, going straight is often the most expensive route. A spacecraft does not aim at where Saturn stands, but at where Saturn will be. Every planet is moving, so the flight is a meeting between objects that never stand still. Gravity assist does not create energy from nothing. It exchanges momentum with a giant planet. The planet hardly changes because it is enormous, while the small spacecraft receives something valuable. So the flight path to Saturn may be longer than the straight distance, but it saves fuel. But for humans, saving fuel with time increases radiation dose and isolation. Radiation in deep space is not like sunlight. It includes high-energy particles from the sun and the cosmos. Some particles penetrate deeply, making shielding far more complex than wearing thicker armor. Too little shielding is dangerous. Too much makes the ship heavy, slow, and fuel-hungry. A solar storm can turn a quiet day into a situation requiring immediate shelter. The crew needs a small refuge surrounded by water, food, or better absorbing material. The third mechanism is air. Oxygen must be supplied, while waste gases must be removed continuously. On Earth, forests and oceans do this silently. On a spacecraft, machinery must replace a planet. Carbon dioxide does not need much to cloud thinking, slow reactions, and weaken decisions. Water also follows a closed loop, from breath, sweat, and waste back into drinking water. The more perfect the loop, the lighter the ship. But one contamination can shake trust in the system. Food is another survival mechanism. Not only calories, but nutrition, psychology, and a sense of time. A meal repeated for years does not only feed the body, it tests memory of normal life. Weightlessness is the next invisible mechanism, quietly changing how blood, muscle, and body fluids distribute. The heart no longer pumps blood upward against gravity as before, so the entire body feels different. Some problems may recover after short flights, but a journey to Saturn stretches far beyond normal. To solve it, people imagine artificial gravity, but rotating a large structure is extremely complex. Spin too fast and it feels uncomfortable. Spin too slowly and it needs a huge, heavy radius. So artificial gravity is not a simple switch, but a small city that must rotate safely. Communication is another hidden mechanism, because voices must cross darkness at the speed of light. When distance becomes too large, a conversation turns into very slow electronic letters. No one in mission control can shout a command and expect it to save a critical second. So intelligence on board must shift from obeying orders to diagnosing itself and keeping stable. Propulsion is also a key mechanism because chemical fuel is powerful but not ideal for every long segment. Electric propulsion can be more efficient, but it usually pushes gently and needs a long time to build speed. Nuclear engines could open more options, but they bring complex safety, political, and engineering questions. High speed shortens travel time, but makes braking at Saturn harder. Slower arrival makes braking easier, but the crew must live longer in an environment that wears them down. This is the journey's trap. Protecting humans makes the ship heavy, and a heavy ship makes the journey harder. Saturn also has a vast magnetosphere and a complex particle environment, not just picture-perfect rings. The rings are not a road. They are countless ice and rock particles moving in their own orbits. A tiny particle at high speed can become a natural bullet against the spacecraft hull. From orbit, radiation, air, water, heat, and psychology, every mechanism is linked. Seen closely enough, a Saturn mission is no longer flying far, but keeping life unbroken. The first hidden cost is dependency. The safer humans become, the more tightly they are bound to machines. The farther from Earth a place is, the more a small pump resembles the crew's second heart. The second cost is mass, because every protective layer must be lifted out of Earth's gravity well. One cannot simply say add more water, more armor, more medicine, because every more has a launch cost. The third cost is psychology, when the ship becomes home, workplace, and horizon all at once. Deep space is not loud. Its long silence is what makes time feel heavy. Isolation is not only lacking people, but knowing no one can arrive in time when needed. The fourth cost is medicine, because a small problem can develop for weeks without a hospital. On Earth, doctors rely on a vast network. On board, that network shrinks into a few cabinets. The fifth cost is microbes, because a sealed cabin is also an ecosystem for very small things. Without natural wind or cleansing rain, skin dust, moisture, and bacteria must be controlled. The sixth cost is repair, because no ground engineer can step onto the ship. The crew must repair equipment they did not design, while that same equipment keeps them alive. The longer a mission lasts, the list of things that can fail begins to resemble the whole ship. The seventh cost is expense, not only money, but years of testing before anyone dares to launch. Every wrong assumption must be found on Earth, because beyond Saturn there is no place to try again. Even success has a price. The crew must accept years of living inside a flying tunnel. The spacecraft may be full of technology, yet poor in the things bodies use to measure life. There is no smell of soil after rain, no wind on skin, no distance for a truly long walk. So the golden doorway midway through the journey is no longer a symbol of exploration, but a test of endurance. One can make the ship larger, but a larger ship needs more energy to travel and stop. One can carry more people, but more people need more air, food, water, and private space. One can automate more, but automation adds another layer of software that can fail. Every solution adds a layer of safety, and another layer that must be trusted completely. And one bad enough event can reveal how fragile the entire balance really is. Imagine a reasonable scenario. The spacecraft has already traveled more than halfway to Saturn. Signals to Earth take a long time to go and return, while the engine bay begins reporting anomalies. There is no huge explosion, no dramatic scene, only a water pump slowly weakening. If it stops, water recycling slows, local heat rises, and daily routines begin to break apart. The crew sends data home, but the answer cannot arrive before the first decision. On Earth, hundreds of specialists could analyze it. On board, a few people must act immediately. They open the spare parts store, find the backup pump, then discover one connector does not fully match. A tiny mismatch, meaningless in a factory, now becomes a survival problem in the void. They can improvise a modification, but every action must avoid debris, leaks, or electrical shorts. Meanwhile, the water system shifts into conservation mode, and ordinary habits are reduced one by one. No one panics, but the silence shows everyone understands the ship has just become smaller. One person repairs, one monitors the air, one maintains communication, and one calculates reserves. This is where distance shows its true form. Not kilometers, but time that cannot be shortened. Rescue cannot launch like an ambulance. Orbit, energy, and time all work against it. Even an extremely fast rescue craft would need a launch window, fuel, and its own survival system. So the faulty spacecraft must become a repair shop, hospital, and shelter all at once. After many hours, the temporary part runs again, but no one knows how long it will last. Success now is not glorious victory, but gaining one more stretch of time. Yet every added stretch of time also spends more supplies, more effort, and more trust. If the fault repeats near Saturn, the decision becomes heavier: enter orbit or turn back. Turning back is not as simple as turning around, because orbit is not a road with an opposite lane. Continuing is not simple either, because entering orbit means locking oneself deeper into the Saturn system. That hypothetical situation shows the greatest risk is not an accident, but having no margin left. In deep space, safety does not lie in courage, but in the number of backup layers remaining. And when backups run out, no matter how beautiful Saturn is, it cannot become a place of rescue. After risks like that, design thinking must shift from can go to can fail and still live. Every critical system needs bypass routes, conservation modes, and repairability with available tools. Good design does not only avoid failure, but makes failure slow, visible, and isolatable. Training must also change. Astronauts must know their ship like sailors know a vessel at sea. They cannot fully depend on the ground. A distant ship must have the authority to decide for itself. That makes artificial intelligence and spacecraft health check software a new safety layer. But software must also be verified, because one wrong decision can spread across many systems. The modern response is to test on Earth what no one wants to learn for the first time out there. Sealed chambers, deserts, ice regions, and orbital stations all become small versions of isolation. Those places are not Saturn, but they show how humans change when the road home is stretched. Technologically, the response is to shrink machinery, increase durability, and make systems easier to replace. Another part is printing or fabricating replacement parts on board, instead of predicting every spare. But manufacturing in space also needs raw material, energy, quality checks, and safety procedures. Biologically, the response is to monitor the body like a system adapting day by day. Nutrition, sleep, artificial light, and work schedules become technologies for protecting the mind. The crew must be chosen not only for health, but for the ability to live together with few options. The farther one goes, the more success depends on very old qualities: patience, discipline, and trust. So designing a Saturn ship is not only mechanics, but designing a minimal way of life. But no matter how good the response becomes, it still does not erase the question of the journey's value. If robots can do most of it more safely, why must humans go there in person? The most common misunderstanding is thinking the problem is only building a strong enough rocket. Rockets lift humans off the ground, but they do not solve years of living in a hostile environment. The second misunderstanding is thinking distance is just a large number on a solar system map. In reality, distance turns every fault into delay, every shortage into a limit, and every decision into self-reliance. The third misunderstanding is thinking Saturn is like a place where a base could be built if reached. But Saturn is a gas giant. More realistic destinations would be orbit or its moons. Even when choosing a moon, humans still face freezing cold, isolation, radiation, and extremely distant logistics. The fourth misunderstanding is thinking courage can replace life support systems. Courage helps humans enter danger, but it does not filter water or stop high-energy particles. The final misunderstanding is thinking exploration always needs human feet placed directly on a distant world. Often, the deepest exploration comes from small, silent machines rather than crude cabins. The problem is not that humans lack ambition, but that ambition must pass through a fragile biological body. The modern turning point is realizing the better question is not how to send people farther. The better question is how to send curiosity, sensors, and robots where bodies should not go. Robots do not need to breathe, do not feel loneliness as humans do, and do not demand daily drinking water. They can fly for years, sleep, wake, measure, and send back fragments of truth. Telescopes also change the game because they can see far without carrying the body far. Uncrewed stations, flyby craft, orbiters, and landing robots can divide the risk. Instead of placing every life in one ship, science can send many small pairs of eyes. That way of thinking does not make humanity smaller. It makes ambition smarter. One day, new technology may shorten the route, improve shielding, and regenerate life support systems better. But even then, Saturn will not become a friendly place for the human body. The universe does not oppose humans with malice. It simply was not designed for blood, bones, and lungs. So never here is not a curse, but a reminder of present limits. Humans can extend awareness beyond the body by sending tools ahead of the dream. And sometimes, the wisest exploration is knowing which doorway machines should cross first. In the end, an uncrewed probe quietly flies along the edge of Saturn's rings. It does not breathe, fear, or remember blue skies, but it carries the curiosity of a questioning species. Behind it, Earth is only a distant point of light, where the human body truly belongs. The golden doorway remains there, not closed, only reminding us that the universe is wider than the body that made us.